Hello, everyone. Welcome to this workshop. My name is Faraz. I'm one of the co-organizers at the summit. It's my absolute pleasure to introduce Jules. Jules is a senior developer advocate at Databricks and an MLflow contributor, as well as O'Reilly co-author of the Learning Spark II. He is a hands-on developer with over 20 years of experience and has worked at leading companies such as Sun Microsystems, Netscape, At Home. He holds a B.Sc and an M.Sc in computer science from Oregon State as well as Cal State. So without further ado, I'm going to hand it over to Jules.
Thank you, guys. Let me just bring up my screen over here so we can chat. Can you guys see my slides? Thumbs up. Brilliant. Well, thanks a lot, Faraz, for the kind introduction. And I'm really delighted to be here for the third time in a row. I must be doing something right for Faraz to keep on inviting me. So I'm really, really delighted to run this workshop for the third time. And it's nice to actually have all of you here. Whatever time zone you are, welcome to the MLflow platform for machine learning. We have loads of stuff today. So I'm going to run through it really fast. And the good thing is that I've given you the instructions on how to get the community edition started. If you can't get things running today, if you don't get to do the labs, you don't have to worry about it. It's going to be something that you will actually have. You can work on it later on as part of the cure for insomnia. So here's what the agenda is today. I'm going to give you an overview of the ML development lifecycle challenges. This conference is all about ML ops, so you're probably going to be hearing a lot of these things throughout the day. And then I'm going to talk about how the MLflow tackles these challenges. What are the motivations and the concepts behind MLflow, 4 components which make part of the particular platform. And then we'll start talking about the first MLflow tracking component, how to use the APIs. We'll go through one very simple example of you showing in the notebook how you actually use the MLflow. And then we'll do that in the Databricks Community Edition. We'll explore what the MLflow UI looks like. And then we won't do the tutorials and exercises because this is normally a 4-hour workshop or an all-day workshop. But we'll just step through the first exercise, and then we'll just move on. And then you can actually do the homework exercises at home because I have a section at the end that tells you how to do the homework exercises. So hopefully that will sort of get us going through the hour and a half that we actually have. Okay, and the link, I posted this particular GitHub link both in the chat, as well as those of you who attended, you should have received that in email. This gives you actual instructions how to set up the community edition, as well as how to set up your local machine for the fourth module or model registry that we actually do. So that link is on the chat. Have a look at it and start enrolling yourself for the community edition. If you can't do it today, don't worry, you can always do that later on in your free time. So I'm gonna make an assertion starting by saying that machine learning development is complex. And the complexity does not necessarily stem from the fact that the algorithms and the math and the concepts behind them are difficult, nor is it from the fact that the languages that you actually use, such as Python or Scala or any of the other language bindings that you actually have to use, the algorithms are difficult, because most of that has been abstracted, and the default classes that you actually get for the algorithms are fairly good enough to give you the default learning parameters so you can actually get started to doing your model. The complexity stems from the fact that the idea of a machine learning development is very different from the traditional software development cycle. So the idea of how the machine model is developed, how it's actually trained, how it's actually tested, how the data is actually used, that is where the complexity comes in. And so the complexity is not so much of the fact that the theory and the math behind is difficult. It is the surrounding infrastructure that you actually need. It is the process of the model idea to production that's very difficult. And I'm not the only one who's actually making that particular claim. You will actually hear that time and time and again in this conference, as well as in other conferences. And most recently, Andrew Young actually gave a very insightful talk about while ML ops is is actually needed in machine learning development, and why is it traditionally different from the AI software? Because in the traditional AI software, you actually have the scope of the project is very much limited. You actually have your scope of the project, you develop the code, you have a CI/CD, and you put it in production. Whereas if you compare that to the software cycle, it's very different because the data changes all the time. You have to do feature engineering, you have to train the model, and you have to train the model by expanding the hyperparameter space to actually get the best tuning parameters. And that's a very experimental, that's very repetitive. You can't just do it in one flow. And then you have to deploy that particular machine into a particular mode and monitor that machine. As data changes, you have to do all that again. And that is very different. And if you compare that to a very old seminal paper that was actually published by Google, by Scully, where you actually see the machine learning code itself is very minimal compared to the external infrastructure that you actually have to support. So as a result of this external infrastructure and the methodology in which you develop software for machine learning, which is quite different from software you develop for traditional learning, this complexity emerges, and you actually need tools and you need frameworks and you need a platform to allow you to manage that, not only in a scalable way, but in a way that's actually easy to maintain as you go from idea to production. And so if you enumerate some of the traditional differences between some machine learning and traditional software, the goals are slightly different, right? If you are a software engineer, you are given a PDF and you're given a functional specification to implement a certain task, and you do that very easily, right? You take that, you implement that, and you deploy it. Whereas compare that to the machine learning, the optimizing task is different. The goal over there is to get a particular metric that's going to solve a business problem that you're actually trying to address. And you have to make sure that you do that in an accurate way, so you are confident about the model's accuracy, so you can actually deploy it. And the quality of the code in the traditional software depends on the code itself, among other things, where the quality of the code over here, or the quality of the model, actually is depending on the input of the data and the tuning parameters that you actually do. And that bit is experimental. You just don't take one tuning parameter and then have an input set or training data and say, okay, we're done with it, right? You have to experiment that, you have to repeat that, you have to explore the hyperparameter space. And the data is very important, because the quality of the data will determine the output of the metric. You know, as the saying goes, that you can actually have the best model, but if you have a poor data, if you have lack of quality of data, you're going to have average results. But you can have good metrics if you actually have an average model, but you have very good data. So that's an important part of it. Secondly, in the traditional software, the stack that you're actually going to use for your deployment environment is going to be limited. There might be a couple of databases, there might be an application server, there might be some firewall and a few databases and so on and so forth, a few languages that the company actually supports, and a limited number of libraries. But with machine learning today, with the proliferation of all the open source tools and frameworks and libraries that come out on a daily and weekly basis, you want to have the ability to pick the best one to use for your model to meet the goal that you actually have. So there is a huge difference over there. And you have to actually support all those things. Your infrastructure has to support all those things in order to be able to do that. And you want to compare and combine the best libraries with the model and the algorithm, so you actually get the best metric. And then the environment in which you deploy your traditional software is limited. You might do it in the cloud, you might do it on-premise, you might in a hybrid environment. Whereas in the machine learning, you have a very diverse deployment environment. You might deploy something on the edge, you might deploy something on the prem, you might deploy something on your laptop, and so on and so forth. So these diverse environments added another dimension of complexity. And so if you look at the traditional building application cycle, you actually have your quintessential data preparation, and then you have a training and your deployment and your raw data. And this is a continuous iterative process. And at each stage, there are different things that you actually worry about. So the first thing you have to worry about are tuning parameters. You know, how do you actually tune the parameters when you're doing data exploration? Right? You might do that in Spark, you might do that in Pandas, you might use Python, you might use certain database or SQL, and they might have some tuning parameters that you actually do and need to persist to do your data preparation. That's normally done by data engineering when they actually build the pipeline. Then there is a tuning parameters. You actually want to have different tuning parameters for different libraries for the problem they're actually solving. If you're doing classification, then you need certain tuning parameters for an algorithm, for PyTorch, or for TensorFlow, or for scikit-learn, for you to be able to actually do that. And if you're using any other libraries, tuning parameter is very important. So you have to do that at a massive scale. The second problem is that you have to do that at scale, right? Today, we have data that's actually coming at enormous volume, enormous space, and you have to be able to do that with scale. And the more data you have, there's a correlation that you actually might have a better universal training set, so your accuracy is more generalized. Your algorithm tends to converge, and you have a better training algorithm. So that has to be done at scale. You have to deploy that particular scale as well. You just can't deploy it on one machine. You might have to deploy it at several machines. So all those have to be done at a particular scale. So you can actually see the complexity arises. The third bit is, how do you actually model exchange, right? If Faraz builds a particular model and he says, Jules, here's a particular model that I built and I want you to deploy this particular model, how is the exchange managed so that I get the same model that Faraz developed on his laptop, that I can actually take it and put it in the cloud, or put it in staging, or put it in my CI/CD environment? So the tuning parameters are the same, the data set is exactly the same, the library dependencies and the versions are actually the same. How do I actually make sure that the model exchange is done in a consistent way without losing any of the fidelity? And then finally, the governance is an important part of it, right? We are living in the world of GDPR and privacy, and we actually want to manage the governance of the entire model from beginning to the end, and privacy is actually important. So you're asking me, well, you presented all these particular problems. You are making a claim that building applications is complex. And why is it that a lot of companies out there, the big data companies, have not solved this problem? It turns out they have, right? They have actually built custom machine learning platforms where they, for the companies like Facebook and Uber and Google have built these particular platforms. They have actually cracked the code to standardize how you actually do data preparation, how you do training, how you do deployment, how you do tracking of experiments, and so forth. The problem is that if you are working over there and if you are working with that particular platform, you get all this for free. But if you leave, right, they're limited in number of algorithms and frameworks they actually want to use. And they're tied to the company's business goal. And so you're limited to the number of frameworks that you actually support, because they're only going to address the problems that they are facing, right? So if you leave the company, you're out of the luck. And so when we were looking at MLflow platform, and Matej Zaharia, who was actually, by the way, giving a talk on Thursday on MLflow and how to do MLflow machine learning at scale, I urge you that you actually attend MLflow Matej Zaharia's talk. He's the original creator of Apache Spark, as well as this particular platform. When we were looking at this particular platform in the initial days, we said how we can actually learn from this machine learning concepts, and how do we actually do that in an open manner. The important is that can we actually do that in an open manner so that people can actually pick and choose the best library they want, languages they want to use. So in order to actually use this and solve this particular problem. And the result was that, okay, we are going to do something in a very open manner, and we're going to modularize it. And we're going to modularize it so that each of these modules and each of these components form a particular address a particular area of that particular MLflow cycle. And the important part was that we want to have the ability to give them the programming languages in which they're familiar with. It's easy for them to come up to speed. And more importantly, we actually wanted to make sure that we support most of the custom traditional ML libraries that people are actually using at scale. And that was the primary goal of saying, we're going to learn from this big kahunas who've actually built this platform at scale. They've cracked the code, but we're going to take that in a manner so that we can actually do that in an open manner. So that allows us to keep on extending this as more and more demand comes in, as more and more areas of expertise are actually needed. And that was sort of built around the philosophy of developers first. Always think about developers first. Whenever you're actually building a particular platform, think about the first principle. Think from the first principle, from the ground up. And so we say we're going to provide them with the APIs so they can actually use the APIs to build whatever they actually want to do that. And APIs has been fundamentally the grounding success of any particular platform. You look at any particular platform that's actually successful, name me 2 or 3, put it on the chat. It is the API first. And the quintessential example I would claim is Unix. If you look look at Unix, how is this actually successful? We wouldn't be standing over here. I wouldn't be giving a talk today if it hadn't been for C interface and it hadn't been for C APIs that allowed you to build enormous applications on top of that. So API first was the particular principle. And the second was the modular design. We didn't want to say all or nothing. We wanted to have it distinctive and selective. So you can actually use tracking if you actually want, or you can use registry if you actually want, or you can use projects if you want. You don't have to use all of them. And that was the flexibility that we actually had in mind. And we provided with you with the APIs, with the RESTful and the CLIs to actually do that. And that was the main design philosophy behind what we actually learned from all these companies and what we actually put forward. So that's how MLflow came up with the 4 components. There's a tracking component, there's a project that allows you to package and redeploy and reproduce the platform. Then there's model, which is an abstraction that allows us to have the ability to protect those models and deploy them on the diverse environments. And this model, MLflow models, also allows us to extend any new libraries they actually want. And the model registry was the last bit that allows us to provision models, the version models, to put models in different stages in your continuous development life cycle. So before we get into tracking, I wanted to sort of give you an introduction of certain key concepts in MLflow tracking. Right, tracking, when you're building an MLflow experiment, there are a few things that you actually want to keep track of. First, you want to keep track of the parameters that you actually use in the algorithms, which are normally the key value inputs for your learning curve, for your number of trees that you're going to use. Those are the input parameters, which are not learned. Those are the static parameters they actually provide. There are some metrics that are going to be computed that you actually want to capture. So you want to track those metrics for each and every epoch, for each and every run. And there might be some tags and notes and information they actually want as part of the lineage, as part of the description, so you can actually track how the model evolved from the initial stages. And then the artifacts are the products of the MLflow experiment. So those could be files, those could be pointers to data sets, the training data sets, the validation data sets you actually use, and the eventual model that will have the weights and the parameters that you actually learn. And those are the artifacts that you actually want to keep track of. But more importantly, you actually want to have the ability to version what source code was used, what library was used, what version of the library was used, what version of the code was used in GitHub. And then you actually want to have various runs. And runs is an instance where you actually run an experiment, and then an experiment is a collection of runs. So those are the key concepts behind tracking. And this is not the case that tracking didn't exist. People used to keep track of these things, but in a very primitive, modular way. Now here's a pseudocode that you might load a particular file, you're actually extracting n-grams, and you're computing accuracy, and you're just logging that thing, right? You could log that to a file, you could log to a database, and so on and so forth. And then you just dump that model into a picker. And so the output of your file might be something like this. But if you ask a very simple logical question, what if I have to expand my input parameter? What if my n changes to 3 and I have to have another set of log algorithms that actually logs that? What if my tuning parameters change? What if my learning curve changes? Now I have to worry about tracking those again and then have another file. What if my libraries upgrade? So if you take this particular thing to the logical conclusion, you can actually see that this tract can be quite intractable. And so the idea was with the MLflow was to give developers a very simple API, right? In that way, you don't have to change your code. You do minimal changes to your code, but you just inject, you just surround, you sort of decorate your existing training code with MLflow tracking code, and then you tell explicitly what is it you actually want to track. Right, so you can do, for example, you can start a particular run, which starts your training run, and then you can log the parameters that you're interested to log. And so what happens is that we keep track of all those parameters and providing the UI to be able to look at each and every run and each and experiment and compare those metrics so you guys can have multiple runs. And this makes your life a lot easier. The amount of code that's actually required for you to change your existing ML algorithm is very limited. You pretty much keep the same thing, but you just inject MLflow kinds of code around it. But even better, we actually went one more step further and created what we call MLflow auto-logging, where you don't have to explicitly log all this thing. You just say MLflow auto-log, and it will ascertain at the time of run what are the metrics and what are the parameters you actually need. So the idea is very simple. The MLflow actually has a tracking server where you actually track all the entities of all the MLflow. You can put it in the SQL database, or your models can go into an artifact store. You set the tracking URI to point to a particular thing, and you start writing your code, and it will just track everything automatically for you. Or alternatively, if you don't want to use all these tracking algorithms, you can just use what we call the MLflow autolog. And the autolog is this new API that we actually have developed, and it will autolog for you all the parameters that it will ascertain the time when it's running the fit to say, these are parameters you supplied, these are parameters which are learned, these are the metrics that I computed, and I'm going to autolog that. And your code now becomes relatively simple. It's very, very simple. The amount of code that the MLflow requires is just one autolog and the model they're actually using. And that will create all the artifacts for you. And the architecture is very simple. You actually have a tracking server that can run remotely, or they can run locally if you're running on a local machine. And you can write this MLflow code in Python, in Java, in R, or REST API in a notebook, or you can actually use it on local IDE. You can run that as cloud jobs and so on and so forth. And so the only thing you actually need to do is you export your tracking URI to say where your tracking server is running. You set that in your library, and you go on. And there is a host of APIs that allow you to do that. So we have the MLflow, which is the Flow and Python API that most of you will commonly use, and it also has the MLflow autologging, so you don't have to sort of worry about like what parameters they actually want to use. For starting, I can just use like MLflow autolog, and if I'm using scikit-learn, it will know exactly what parameters you sent to your algorithms and what were the parameters or learn parameters computed, what the metrics were there, it will log it for you. There is an MLflow model flavors API. If you actually go to documentation, these are all the models which are currently supported in MLflow, which means that you can actually use this MLflow algorithm, or you can use this MLflow models to create your polygonal model. And then there is the final bit, which is the MLflow client tracking API, which is more low level, that allows you to do create, read, update, and delete operations on your experiments, on your runs. And this is something that you're going to use if you're more of an advanced user where you actually want more control. But most of the people who are starting with MLflow will probably use the MLflow Flow API, which we're going to see in our lab. And there are different ways you can actually run MLflow. You can run MLflow on a local host. You don't have to use Community Edition. You don't have to use Databricks cluster. You can just run locally. And all it does, you don't need an MLflow server. You're running locally to pip install. You run locally, do the MLflow, and it will run locally on your machine. And it'll create a directory called MLruns. And then within MLruns, you will actually see this directory structure, and each under the artifacts which are created, which are the models and the ML5. The certain metrics are actually created, the parameters are given as well, and then all the tags that you might actually put in there, those are updated as well. So these are things that you can actually do it locally. And as I say, it's very simple. MLflow UI can also run on a local host with an Alchemy server. And when you use an Alchemy server, which is the SQL compatible one, it creates the MLruns directory. It will only keep the artifacts over there, and everything else is actually stored in the local SQLite database. And so the flexibility is actually enormous when you're using tracking server. You can actually use in a number of combinations. And let me show you some of the combinations that you can actually use. So scenario one is that you actually want to use localhost. You're typing stuff locally, and you're going to use it. And when you use the MLflow code, all the experiments are going to be stored locally on the disk. The client will actually use the local artifact repository to store all the artifacts, and all the runs are stored in the local file store in the file system. Or you can actually use localhost with the Alchemy database, whereby now all the MLflow entities are not stored on the file system, because if you have hundreds of experiments, each experiment will require a file descriptor, each parameter will require a file descriptor. Pretty soon you're going to run out of file descriptors. So you can actually use the Alchemy database to store all your MLflow entities, and that way now you actually have some scalable solution in your localhost. Or you can use a tracking server running remotely, and then you can actually do that as well. And so these are the common scenarios that people use. This is the most common scenarios that people have actually used. So if you're using it in production, or if you're using it in the cloud, then you'll have your local client, which is using the MLflow APIs, and it talks to the remote host. And the tracking server then will store things in either Postgres or MySQL, whichever database that you provide. And then you can actually upload all your artifacts remotely to an S3 or an Azure or GCP. So this is a scenario that some of you might use, but people who are actually getting started are probably going to use things on the local host. And as I said, the tracking server uses different storage. You know, for backend store, we can use file store for running ML runs if you're running a local host. We use all the SQL compatible stores. MLflow plugins is a way for you to customize your meta stores. And then the artifact stores could be any of these S3 buckets that you actually use. And so again, this I already gone through the API, and the model flavors actually has the APIs that allow you to log a model, to load a model, to load the model as a Python function, and also allows you to track the signature. So for example, if you do an auto log of a Spark model, you can actually infer what the signature is going to look like, and we actually track that. And this is good for validation. So when you're checking your model in production, and if the input parameter signature is different from the one that model was trained, you will get an error. So this is a good way to keep track of what the signature is for your inferred model. Some of the things that the API provide you is the ability to actually do model interpretability, right? So you can infer the signature, and you can also log the model with the interpretability of a SHAP image, so you know what features in the experiment run determine the outcome of the image. So this is a new set of APIs we introduced, which is called SHAP log explanation. You take the model and you provide some of the features, and it will give you the feature breakdown of what feature were responsible, or what feature triggered your model to act in a particular manner. We also have the ability to work with PyTorch, and this was some of the new integrations that we actually did with collaboration with Facebook. So now you can use PyTorch auto-logging Lightning. So if you're using PyTorch Lightning, you can use auto-logging. You can take your PyTorch MLflow log model and convert them into Torch script for better execution, and then deploy them in the Torch serve deployment environment using the MLflow deployment PyTorch plugin. And this is very simple. All you do is you do import PyTorch learn, set the auto login to be true. You create your trainer, and you fit the model, and then all that will be automatically logged for you. If you log the string, you log the parameters, if you log the metrics, all that is automatically logged for you. Your code becomes very simple. So the whole idea and the whole premise behind developer first, API first is ringing true in some of the things that you actually can do with MLflow tracking. And this is to very easily take your PyTorch model that you actually have and then deploy them on the Torch serve environment. So this gives the ability to take your PyTorch, if you're a PyTorch shop and you have a Torch server running somewhere, you can actually deploy those models over there. And finally, I mean, you know, we talked about what are some of the modular components which greatly simplify ML lifecycle. It's easy to install. You use a great developer experience. And that's the whole idea behind the MLflow tracking, is that you actually get the ability to track the experiments you actually want. And very easy, just do pip install MLflow, get started. Look at the docs and examples in MLflow, peruse through some of the code examples that we have in the GitHub, join our Slack channel. I am normally one who answers all the questions in the Slack channel, and try the MLflow tutorials that we actually have. So for that, let's go to our tracking. But before we actually go there, I want to make sure that you guys have any questions. You guys, any questions? Let me just do the chat. I know I went through a lot of stuff here today. For us, I don't see a chat here.
Hey, there is one question. If you just want to read it out. Okay. Got it. Are we going?
Go ahead.
Oh, sorry. So the question is, are we going to talk about authorization on MLflow?
Good question. Good question. The open source version of the authentication authorization does not exist right now. The managed version actually has that behind the IAM roles that you actually do in your cloud provider. So right now, the HTTP requests that actually go to the tracking server is completely on the clear. You have no authorization at all right now. What people actually have done when they deploy this in production is they put it in front of a reverse proxy, or they put it in Nginx, and then when they get a particular request, they can authenticate against a set of groups, a set of roles that they have created. And once that's allowed, they can pass that to the tracking server. So that's the one way of doing an authorization and authentication. It is not part and parcel of the open source MLflow, but it is built into the managed enterprise tracking server, because there you are actually using the cloud provider service. In the case of AWS, we use IAM roles. So if you're part of the particular group, you'll be able to do certain things. If you're part of a certain group, then you might be able to administer the model registry and so forth. The short answer to the question is that not in the open source, but yes, in the managed source, managed version. Sorry.
There's also a follow-up question to that. Is the same situation? Is it the same situation for multi-tenant support?
Yes, I mean the multi-tenant support again depends on how you actually deploy it on your deployment environments, right? So if you are deploying it on a Kubernetes, I would use either Seldon Core or I would use KF Serving, right? So MLflow server would just run, and the multi-tenancy is not part of the infrastructure, it's part of the infrastructure that you actually provide. So whatever your serving environment is, if it's running on a Kubernetes, and that could be in a pod, and you can have multiple pods running. And that way you can actually have multi-tenancy over there. So the tenancy is not part of the MLflow, but it's part of how you actually deploy it in the eventual infrastructure.
Cool. Fatima was asking if you could please share the link to the slides in the chat.
The slides are all in the workshop. If you go to the link on the GitHub, you'll see a directory called slides, and within the slides you have the PDF version of that. So if you have that link open on the GitHub workshop, I have a directory called slides, and under the slides I have a PDF version of all the slides.
There's also a couple of more questions.
Sure.
Did you go through the questions? Yeah. So Martha asks, what's the performance of MLflow when used by large teams as a central service? Is it able to handle big amounts of experimental runs?
Good. I think those are good questions. I think the number of issues you have to think about, right? If you're running it locally on a local host, you don't worry about performance that much, because you might be running maybe a couple of hundred experiments. As I said earlier, when you run on a local host, the artifact store is your local file system. And under the local file system, as I showed, that it creates all these different directories and different files, and each file and each directory will take up one file descriptor. So on a Linux, you would eventually run into over 10,000 file descriptors. And if you have to do an ls of a directory over 1,000 directories, you will see a performance there. In the cloud environment, right, most of the people, the way they actually use that is that they actually have the ability to run that MLflow tracking server on one machine, and then they have the Postgres running, or the MySQL database running on another machine, and then they have the artifact store in an S3. In terms of number of connections, yes, it is fairly scalable, but it's nice to actually have the ability to actually have it behind a load balancer, right? Because the MLflow tracking server is stateless, but as long as it's talking to the same database, you're actually fine. So if you have a load balancer that you actually keep in front of your Nginx, and then you just federate, or you just route those experiments across the request, then you're actually fine. So you can scale horizontally behind a load balancer, as long as the tracking server is all logging to the same artifact store and the same backend store, then you can actually scale to thousands of connections. And we, in the managed version, obviously runs behind our infrastructure. We have thousands and thousands of connections coming in, and people are logging and registering, hundreds and thousands of models. So we actually haven't had any problem there. And if you want to sort of scale it, because of the fact that it's stateless, you can actually do that in that particular manner.
That's great. Ruby asked, you might have already answered this already, but they ask, does MLflow have the ability to track models in production, or a secondary package is required?
When you say track, are you talking about monitoring? So if I answer the question correctly, is MLflow can MLflow track models in production? Or what you can do? Right. Yeah, what you can do is monitoring is not currently part of the MLflow open source. Monitoring is something that you actually have it do it externally. So when your model does a predict, one thing you can actually do is you can track that, right? One of the good things about tracking experiment is that you can actually load that particular prediction. So one way that you can actually do model drift, or you can do data drift, is every time you get a prediction, you track that particular prediction into an experiment or into an area, and then that becomes your data that you can either feed it to Grafana or you feed it to Prometheus, so that you can actually start monitoring the data drift or the performance of the particular model as it happening. So that way you can actually track the amount of time it actually took for the inference, or the latency for the inference, by tracking it. And then you can use any log API, you can use track that as a log data structure as an experiment, and boom, you just put it away.
That's great. We have one more question. Arman asks, anything on the roadmap WRT model governance?
We at the MLflow, at the Spark Summit, we sent out a survey to say we are planning to do MLflow 2.0 in design phase. We are looking for input. We are looking for things that you actually want to see in MLflow 2.0. So I can actually, I'll post a link at the end where you can actually include that as part of the survey, because we're in the process of planning to create 2.0, and we really would want to get the feedback from the community. What are some of the things which are missing that you really like to see as part of the MLflow, both open source as well as the Databricks version of it?
That sounds great. And those of you who are also asking about the slides and the link, we will be following up with those after the summit. So we'll send you the video as well as the links as well. Yeah, as I said, the slides are in the directory on the MLflow workshop. Okay, I'm going to go on to the next to the lab, or at least to the workshop in Databricks Community Edition, because this is a long thing, and I want to make sure that you guys, at least I covered the 4 modules. Whether we go through the exercises or not, something that you guys can do it later on, but I want to make sure that you got the concepts right and you have the material at your disposal, so you can actually go and work on it on your own. So let me go to my Community Edition. I'm assuming that you guys have been able to log into your Community Edition. Okay. I'm assuming that some of you are actually having trouble. So here's my Community Edition. So when you log in, assuming that you, sorry?
I'm having delays too.
Yeah, yeah.
Quite some load on it.
It could be that everybody's actually is logging at the same time. That's why I actually wanted this link to be sent to you earlier. So, but again, don't worry about it if you can't get to it. I'll walk through it very slowly, so you actually have an idea about that, and then you'll have the link to it. So once you actually even leave the class today, you will have Community Edition. You can take it to your grave as well if you want. But this is sort of the Community Edition that allows you. We actually changed the UI quite a bit, and when you log in, you actually get this welcome window that gives you the ability to look at what are some of the things you have currently worked on. The left-hand panel that you actually have are high-level operations you can perform. So we're going to go ahead and you can actually create a particular notebook or a table or a cluster. And I want you to go ahead and create a cluster and choose your cluster name that you actually have. So I can use JSD TMLS, and then choose the cluster name to be either 8.3 ML 8.3. Make sure you use 8.3 ML Scala 12 and the Spark Edition 3.11. So this will give you the ability to run MLflow because and with other libraries that you actually support. Once you do that, you will actually have the cluster. So let's go ahead and create that. I don't want that. So this is my cluster that I have. And then when I go to my workspace, you should see the shared and users. Click on the users. On your user, whatever login that you actually use, you will have your email address over there. And then you'll have a whole bunch of directories in here. You might not have anything because you actually haven't done anything. So the first thing you want to do is you want to load up the DBC files that we actually have, the files that I've distributed in the tracking. So this is what you actually do. You go down, you go up to the your login name, and you use the pull down menu, and you do an import, right? When you do an import notebooks, use the URL. And then I'm going to do is I'm going to go to my tracking to my dmatrix GitHub, and I'll click on tracking, and I'll go to the Databricks notebook, and I'll go MLflow tracking DBC, and I'll take this URL, cut and paste, and I'll go back to my community edition. And I type it in and I do an import. And when you do an import, what will happen is that it will import the entire directory, and you'll have this directory called MLflow tracking, right? And once the directory is imported, you can actually go into the directory and look at the file. And I'll click on the file. And this is your typical notebook. This notebook is no different from a Jupyter notebook you actually use. It is the same way of having marked symbols and so on and so forth. So what we're going to do is I just made sure that I created a very small regression model over here to really exemplify and to show how you can actually use tracking APIs as a way to do it. Right, so we're going to go over here. And what we want to do is we have this bunch of features. We have petrol tax and cents. We have a per capita income of the US dollars. We have a paved highway number of miles. And then we have a population with driving license. And we're going to predict what the consumptions are going to be in gallons, millions of gallons per year in the 48 states for which we actually have the features. And we're going to call that as a regression model. Now, when you actually have a problem of bad consumption, this is a bad problem to have. Anyway, so the solution is that we're going to use a few metrics that we actually compute, and we'll find out which is the best experiment that we ran, and what are the root mean square error, and what are the R square error, and so on and so forth. So we'll track those, and then we log those as part of the experiment. So the first thing I'm going to do is I'll just warm up my clusters. I'll just add 1 + 1. And this is a Python notebook. And the way you do that, you can either do a shift control to go to the next cell, or you can actually just use the little arrow over here that you actually have for little arrow here to run this particular cell. Okay. Now, the other thing is that what I've done is one of the things you can actually do in this particular notebook is that those of you who come from the engineering background, you actually might want to sort of modularize your code. So you might want to have setup code. You might have some classes that actually run somewhere else in this particular manner. So you can actually just create this particular classes. If I go to my workspace and I look at my setup, okay, I'm having some interesting issue.
Maybe a quick link, the README files in the GitHub repository point to different versions of the clusters. They're a bit outdated, so that might cause confusion.
Okay, there we go.
And
no, I think it's
selected.
Yeah, I think it's just taking longer because we're all hitting at the same time. I mean, I can switch it to my managed version, but let's go through this exercise. So my class setup over here. okay, this is what I'm gonna do, right? I think we're all hitting it at the same time, and this is causing interesting problems. I'm going to switch to my managed versions. I think we're just having some issues because all of us are at the same time. So I'm going to go ahead and import this over here. Okay, so it's the same notebook except that I'm just running on my setup cluster. So I'm going to go ahead and run this particular notebook. And if you look at the contents of this notebook, all I have is a bunch of classes. I go to my setup. My util class is just nothing but a static method class that I actually have. So that way my main notebook just doesn't become too cluttered. I just have all these different plots that I actually use, the directory functions that I have, and these are my utility classes that I actually use. If you look at my the other setup, regression class, it's the same thing. I just have my RF model as a class. I've created create a new instance. I have a model property, and then I have my entire MLflow. And this is where all your code is going to be, right? So this is my start MLflow run. This is how we actually start a particular one, and all my MLflow code is over here. The rest of the stuff is going to be the same thing that you actually would train a particular model, except that I'm just surrounding this MLflow run with the start run, and then I'm just logging all the parameters that I actually need over here. So log my metrics, compute the plots, log those particular plots, and so on and so forth. So this is the gist of my particular code. And if I go back to my workspace, I ran this particular class, and now I actually have all the utilities and everything have come into the scope. And I'm going to go ahead and load my file, my pandas file using utilities. And you can see the data set looks pretty simple. I've got 5 features. I want to predict this, and I have 4 features. This is my label that I want to predict. And I'll just go ahead and do my described statistics here. And that sort of gives me the idea of what my data looks like. My mean is about 576. I want to make sure that when I compute my root mean square, it is a lower percentage of that. And then this is my entire training code. You can see that I test over several parameters. I create a different number of trees, and I create a new instance of it, and I just use MLflow run to go ahead and do that, right? So this is our main code over here that actually do that. Now, when you run that, you will notice that there is this experiment bar up at the far right corner. It's getting updated in real time. And what's actually happening is that MLflow is keeping track of all these particular experiments. So I run that, and I've created my graph, and I can see as I increase my number of estimators, I'm beginning to see that this actually model converges, and I get a fairly good RMSE for about 60, and I can actually now go in over here and look at my experiments. If I keep on experiment, I'll see that on the far right side, I have a summary of legend of all the experiments I ran. For my maximum depth of 10 and estimators, I got my root mean square error over here. The models these are the models that I actually created. So I ran three runs. I can go this particular experiment page, and I get this entire flow of all the experiments that I run. I can actually go ahead and click over here to add notes that I want. And this is good for provenance, because if you want to give a description of how the model evolved, you can actually type in your HTML code. You can type in the history of these notes over here. So that's a good way to keep track of what the model is comprised of. This is what I talked about, tags and all that. And now I actually have in a tabular form all the experiments that I ran, from parameters to metrics. And so I got the best metric over here. It seems like probably they're pretty close to each other, 60, 62. So I can compare those. I can actually compare, let's see, the 3 over here, and compares those runs. And when I compare the runs, I actually get a scatter plot. I can compare a contour plot that actually gives me the ability to see what the contours look like. I can change and add MSC and RMSE and choose how the contours look like. I can look at the parallel coordinates. That gives me the ability to know how it actually performs. So all the different things you can actually see. I can go to any of these and click over here to see how they actually performed. Where all the experiment, this is my first model, second and third one I cleared. I can actually choose more than one, so that we actually have a visualization of how the actually metrics perform. So this is a good way to sort of compare and contrast the experiments that I actually have. And as you can see, I've got 5 runs. I have the ability to look at the source to find out where it is. This was in my GitHub location. The models were actually created. If I go to this particular, click on this particular model, you can see what was loaded. I can have notes and parameters. These are all the values and metrics that's computed and logged. The tags, if I have any tags, I can actually add tags that I want over here. And then this gives me what the artifact looks like. Now you can see that I have the ability to take this particular code, just cut and paste and use that to experiment, load that as a PDF or load that as a payload function, and we do that in module 3. So that the essence of what the experiment is all about. Any questions? If you guys are running into the community edition, don't worry about it. When you go later on, when there's less load on it, you will be able to run all those experiments seamlessly. So before I go on to the next section, I think we're running out of time. Any questions? Excellent.
How does the integration to Databricks work compared to the imports? Like where does the hook take place that you have the experiments show up in the
so this is all integrated within Databricks, right? Also, when you run this on Community Edition or on the Databricks, the model, the experiment, and all that is actually already integrated. We are running that. All the experiments are stored on the MySQL database that we actually run on AWS. This is on AWS. In Azure, you have SQL Server, MySQL Server, and then all the artifacts are on DBF on S3 buckets. So this is completely fully integrated. You don't have to worry about it. If you're running the MLflow version of it, then you would have to worry about where you actually want to store the artifacts, and you create that by invoking MLflow server with the artifact root path and the tracking server path. So over here, you don't have to worry about anything. Everything is just managed for you. You just go in there, log in, and start running both on the Community Edition. It's limited on the Community Edition because you don't get model registry, you don't get authentication, you don't get authorization. But over here in the managed one, you get pretty much the full bowl of all the integrations that you actually have. Did I answer your question?
Partially. Like
okay, what was
if you import the model there, there's going to be some location where you tell that this is a storage that Databricks can look into to find your experiment runs, right? Like some place of connection that knows where to look, because we just imported the DBC file.
Good question. By default, if you run the model, and when you save the model, it's going to store on the DBFS, which is our file system running on AWS, because that's the default artifact store. If you are going to use if you're going to use, say, another artifact store, let's say you're actually going to store something on NFS S3, why would you want to do that? That's up to you. But let's say hypothetically that you want to use the artifact store in something other than DBVS. You can actually provide that as part of the MLflow integration, where you say my artifact store is going to be here, log my artifacts over there, and then the MLflow client will look at the artifact and will say, okay, I'm not using S3, but I'm using foo, right? And do I have a libraries for the foo to upload my model, right? To upload my artifact. And it's the client that actually, it's not the tracking server that actually does saves the artifact, it's the client. So on S3, it's the Boto 3 client built into the MLflow client that says, okay, I'm gonna upload the artifacts into S3 using the Boto client.
And the notebook UI just says, okay, the experiments are being scanned in the default folder, so it shows that they're there. Okay.
Yeah.
Just,
so when
that's clear now.
So right now, by default, everything is stored in MySQL on Databricks and S3 on AWS. If you're running on Azure, then it'll be Blob on WhatsApp, and then if you're running on GCP, it'll be the GS store.
Cheers.
Okay, let's move on to the next one. Okay, the next one is projects. I'm going to quickly share my screen over here. So the next component I want to talk about is projects. And again, motivations behind why we actually introduced the idea of projects and how do projects are executed on Databricks. We won't go into it because at the time, I'm just going to skip over it and let you guys run on it later on. And then explore the UI and do the tutorial. But the idea over here is I wanted to make sure that you guys understood what's the reason behind projects. And this was, if you remember the slide when I talked about the reproducibility. So if Faraz gave me a model, how do I can reproduce that? And that's the whole idea behind that. And so the second component of MLflow is called MLflow project that allows you to package things, your entire code, in a one unit of execution. Think of it as one unit of execution that you can actually take and then run it in the deployment environment or in the target environment. And it'll reproduce the environment for you and import all the libraries install all the libraries that were used, or the versions of the library that were used to create the initial model and the parameters, so that way you can reproduce experiments. And this is actually good to share that publicly. If you're writing a research paper, for example, if you're in the academic and you're writing a research paper, you create an experiment, one thing you can do is you can create this particular project, put it on the GitHub, and you can share that with your readers. So it's a lot easier. Now, as I said earlier, I think the reason behind the premise and the principle behind MLflow was to make sure that we support a diverse set of tools and we support a diverse set of environments. And the whole idea is that we wanted to support the latest and the greatest libraries that you actually want to use or you desire to use. And we want to have the ability for you to actually deploy them in the target environments of your choice. And this introduces a problem. How do you actually reproduce that, right? And there are kind of three problems, because mainly, each particular project might have a generic way of bundling a particular project and using that to deploy that in a particular environment. So if you actually have n number of projects, you're going to run into n times n number of ways to figure out how to bundle a particular project. Another problem is that people normally either run or develop on their local ID or on the program environment, or they might do it on a cloud. And each of these might have a different environment. And how do you actually make sure that what you developed or what the environment in which you developed is captured in that particular project, so that if you share that with somebody else, then you actually have that particular environment. Even though you might capture the data and the metrics, but the libraries might be different from your local environment to the target environment. And so this sort of result created a problem. How do you actually reproduce that? And so the solution was that we said, well, what about if you actually encapture the entire project and capture all the code and all the configs and all the dependencies that you actually have and all the data references that you actually have in this called project spec, so that you can take the project spec and execute it locally, or you can execute it remotely. Think of it, the best knowledge I can think of it, and I'm going to date myself over here, is to think of it as a makefile or as a Docker file, right? Where you specify everything you actually want. And when you execute the makefile, you execute the Docker file on a target environment, it will fetch the appropriate library based on the architecture it's using and the versions it's using, and it's going to create a unit of execution for that particular target environment, and you got to run it. And so we support right now three environments, right? You can use that as a Conda environment, or you can create a Docker image of that, or you can just use it locally on a particular system. And the idea is very simple behind the project, really. It is that it's nothing but simple a directory. And a directory has a tutorial. I mean, a directory has a name. We call it MLflow project. And under that MLflow my project, you would have a file called ML project. An ML project has a YAML kind of syntax. It'll be the name of the particular project, the Conda environment that encapsulates all the configurations that you actually need. And there'll be a set of entry points. And these are the entry points that your main execution will actually use to take that as a parameters. Now, there are some default types that you can actually use, or you can actually override those with parameters. So that's one part of the project, which is the essence of a project file. The second bit is that you can actually run this now using the command line, or you can actually use that running the MLflow APIs. This particular project resides on Git, and you provide the parameters you need. And if you don't have the default parameters, you can actually override the default parameter with the -p epochs, and you actually run that. The second bit of the project is what we call the Conda YAML, and the Conda YAML file is nothing but the capturing of all the dependencies that you actually need, right? So if you're using that in a Conda, what packages do you need? What Python version you actually need? How are you going to install it? What was it actually used to build it? And that sort of captures the essence of what your config files are. And then you actually have a bunch of files that you will need for running your program. And the anatomy of a project execution is very simple, right? You run this particular thing using MLflow GitHub project example 1, and it's going to fetch that from that GitHub. It will create a Conda environment, and it will activate that environment with MLflow, some unique UID. And then it will install all the packages that is actually listed in the dependency of the Conda YAML. So over here, by installing the packages, you're recreating the environment in which you initially created the particular project. Once it's activated that, it's going to go ahead and now execute your training code. And whatever your training code is going to be now running in this activated Conda environment, that will reproduce the results of the model that you initially trained with that code. So that really is the essence of it. And how do you actually build the project? Very simple, right? You create this ML project file, you populate that with the entry points, your default parameters, you add your Python code that you actually do. You create a Conda YAML file that you have all the dependencies that you actually need. You create a GitHub repository, publish it, and then share with others who can actually test it. Very simple. And this allows the MLflow projects can be shared publicly, which is different from model registry. We'll get to that. But that's the whole idea behind that. And how much time do I have? Okay. And MLflow project, like all the other components that we have, has the ML libraries, it has the CLI for you to do that, has the APIs to do that. So you can actually do things locally on your command line, or you can actually do it remotely. And any project, you can actually have hierarchies of project. And the way you actually do that is by providing, a # subdirectory. And then each subdirectory will actually have an MLflow project that will actually execute that. And it's a very powerful tool in your ability to capture a project and run it as is. Any questions over here so far? Let me see if I can check.
Yeah, there's one question.
Yeah.
Well, there's two now. Is it possible to use ML project with other package managers like Poetry? If not, will it be supported soon?
Can you run? Let's see. Can you let me see? Is it possible to use ML project with other package managers like Poetry? If not, it will. I've never tested on Poetry. Actually, that's a good question. Right now, MLflow project is very much dependent on MLflow and on Conda. Now, given the Conda environment is going through its license re-registration, and so we are reevaluating what other external projects we can actually use. And I would love for you to include Poetry as part of our MLflow survey for 2.0. I know we're going to look into pit environment. We're going to look into possibly what was the other one? Mamba, I think it's called Mamba. Yeah, Mamba is another one, which is like the equivalent of Conda, because Conda now is going to charge you, and we want to make sure that people can actually use it openly. So, quick question to answer: no, I don't know about poetry, but it would be nice that we can actually project. Right now, it is very much dependent on the Conda. Our models are created using Conda YML, and so when you reproduce them, we are using Conda. So come MLflow 2.0, we have to revisit this particular project. So it'll be good to have the ability to run this in other package managers, including poetry.
There's one other question. Can you also reproduce a run that trains a model in R?
Good question. I've never tried R. I know we support R, but I think this is mainly for Python right now. There's a way you can create R models and R API, but I'm not sure if you can actually do that with R. No, I don't think so. But I'll check. I'll check that. I'll make sure. Let me see who asked that question. Willie, right?
Willie, yep.
Okay, Willie. Yeah. Okay. I'll make sure that I don't think so right now. The support of R is limited to tracking and models deployment, but it's not part of the projects yet. Okay. Yeah, go ahead.
There's one other comment was Jack was just commenting that this is for one person managing multiple projects, but our use case is a team of people working on one project.
I mean, this can be both, right? You can actually have one project that you publish it and multiple people are managing. If they are managing, the idea of a project is not like as if you have multiple people who actually manage the project. The idea of a project is a bit of a misnomer in that you use the project to share your experiments with other people to reproduce that, and we've just called that particular project. So it's not project in the sense that you would create a particular project. This does not preclude you. Jack, from sharing that with multiple people who are going to use this particular project. And since this is going to be part of the GitHub, obviously, if it's something that you have publicly published it, and if somebody wants to create a PR request, and you have the sole authority to either accept it or reject it. But multiple people can work on a project since this is part of a GitHub. But the idea of the project is to reproduce your experiment so you can share that publicly with other people.
Great.
Okay. So let's move on. I think we don't have that much time, so I'll skip over the project experiment. You can actually run that when you actually have the time. So let me move on to our third module. Okay, so like I said, the third module is the MLflow models. And again, I'm going to go through the same thing in terms of what I talked about in MLflow projects. And the motivations behind models is no different from the motivation for, say, the model projects. We wanted to have the ability for us to have multiple people, multiple libraries use the particular MLflow model. So how do we actually do that? How do we create that? And the idea behind model was, again, so that we can actually use multiple libraries and deploy them in different serving environments. And again, the idea is no different from MLflow project. We wanted to have all these libraries that you see on the left-hand side to support as part of the ML frameworks. And then on the right-hand side, we wanted to have the ability to take those models and deploy them, either as in a Docker container, or if you're using Spark, deploy them as a Python UDF or a Python model where you can actually do inference in batch and streaming, or you can actually create a Docker environment and then put it on either SageMaker or KF serving or Kubernetes or on Azure ML using the Docker container. And how do you do that? Again, we actually had the same idea of same problem is, people have libraries have different way to create a particular model file and package it and then deploy it. And we didn't want it to have this end-by-end combinations. And again, the idea behind the motivation behind this was to, what about if we abstract that away? We abstract it. We computer scientists and we software engineers like to solve problems by putting abstractions on things of layers and things on top of that. And so the idea was that, okay, let's take these MLflow models that we actually have that we want to support for all the frameworks that we have on the left-hand side. And then we would create this version called, this format called MLflow model format. And we will always create two flavors of the particular model. One flavor will be the standard native layer, and the other one will be a wrapper around the native layer called Python func, that you can actually load that as a Python Lambda function or Python function in any Python environment and strictly run that as an environment in any of these things. And so in order to do that, we actually had to somehow create these two particular flavors that gave us the ability to say, okay, we'll capture this particular flavor in the native flavor. We'll capture all the dependencies that we have. We'll capture what libraries that we actually support and how we actually load that using the native versions of the library to load that model. And we'll have a Python function, which is a wrapper. And then the idea was that you actually provide a very common set of consistent APIs to each and every model that actually have a generic methods, log a particular model. And we would know that when you log a particular model, we're going to log the native model as well as the Python function. When we'll know how to load the model again. How do you save a particular model? How do you add a new flavor? And then if this model is supported in the auto logging, we'll use auto logging for that, and it will automatically load the model for you. And these are the libraries that we actually have on the left-hand side that we currently support, and we're extending more and more libraries as more and more libraries come into prominence and people actually want to use it. And what we do is we just create this particular abstraction, and then you have the ability to do your tracking using that particular model, right? And the idea is very simple. If you look at, for example, when you do a Keras log model, what we do is we create this model directory file, and underneath there's a conda file that actually tells the model abstraction libraries how to actually use that particular model. And I say by default we create two kinds of models. The Keras model will be the native model, and this can somehow be created using Keras native format, and then it can be loaded using the native format libraries. We also create what we call a Python function version, where we actually give the ability to load this particular model as a Python function, and then use that either as a UDF or use that as a Python function to do the predict. And then there's some other meta information available with that. And we also capture in that particular same directory the conda.yaml, which is no different from the conda.yaml you actually saw in project that has all the dependencies. So, we make sure that those dependencies are present in the deployment environment where this particular model is deployed. And then the great thing is that when you use any of the libraries, either say MLflow Keras log model or MLflow Scikit log model, we'll actually have the model format create two versions of that, a PyFunc version and the model flavor version. And then whenever you actually want to use this particular model, you just use the MLflow load to load that particular function as a Py function, and then use the predict method on it and input a pandas data frame. Or you can actually use MLflow Keras load model, which is a wrapper around the native library that calls the predict function, and then you can send the input as a tensors or whatever the tensor file input that your model actually requires. So this gives you the flexibility to use this model in two flavors. And the important part about this, the corollary of this, is that now I can use these model flavors to write any of these MLflow models that I actually have. So I'm using Spark, or I'm using scikit-learn, I'm using PyTorch, and then I can load those functions, and I can load those models as a Py function, and then use the predict to do the input to do the inference. And this is a very, very powerful concept. You will see that in if you have the time to do the exercises, that allows you to actually do that. And this now gives you the generic way to use the Python model as a Python function in any of your code, or you can actually use in the Spark environment. You can actually just use that as a UDF and then do the predict on the features that you actually have. And then finally, what if there's a library that you actually want to use that doesn't exist, right? How do you actually use that? Well, one way to do that is that you extend this particular, you create a particular class and you extend the Python func model as a base class. And then you implement 3 functions that it requires. Predict is the one that you actually need. And then you embed the model that you actually is not supported by MLflow within that particular class. And then you create a predict function that actually takes the input that you actually want to predict on, and then applies that as a lambda function to the inherent model that you have actually captured. And this becomes a lot easier now to support libraries that you don't have support for in MLflow. And here's a very simple example of how you actually do that. In your MLflow run, you actually create an instance of the social media analyzer you actually want. You create a MLflow start run, you load the particular model, you do the inference, and it's going to call the underlying ML module class for you, and you can actually use that as such. So this actually gives the ability for you to extend the MLflow model to use any models that you not support, or the libraries that support. So if you're using Hugging Face or some of the other NLP libraries that you actually want to support, you can actually do that. And then you just load that particular function again, and then just load the parameters, and then do the inference using the predict function. So just to recap, I know I've thrown a lot of stuff to it. Again, just like any other modules, we make sure that we provide you the APIs to be able to read that, to create that, and to use that in the MLflow CLI. There's a tutorial over there. Again, in the interest of time, I think I only have 10 minutes left. Are there any questions? Let me see if I can go to the chat window here. Okay, I don't have any questions. I think we have 10 minutes over here. I think it's important for me to talk about MLflow registry. I think it'll take me 10 minutes to do that. And again, I apologize because of the timing. We don't have enough time to run through the workshops. So let's go to the last bit here. Okay. Here's the last module called MLflow registry. Now, I mean, registry is an important concept that actually came much later on when people were deploying models and they were keeping track of models locally or on GitHub and creating versions of it. And it can become a bit intractable because model registry is an important part of your entire model lifecycle. You want to have different models of the versions. You want to have different stages of the model of the version. You want to deploy different versions of the model in MLflow so you can know what version is running where. And so the idea behind that was to provide a central repository to annotate, manage models in the central repository. Now, model management problem is simple when you actually only have 1 or 2 people working. You have, a model developer is going to create some classifier or some regression model that they're going to create a versions of it and then create those and put it on GitHub, right? Which is fine if you have 1 or 2 people working. That's a simple form. There's an old problem of working with network files. But I think the problem becomes more intractable and needs a more easy solution, a more manageable solution when you actually have a very large organizations and you have data teams, both data engineers and data scientists working together, and they are creating many models per day, per week. How do you actually find out what is the best version of the model, right? Where do you actually find out? how was this model trained? How do you actually train this particular model? What is the governance? Who actually trained this particular model? Who approved the model in particular different stages? And how can I track the documentation for governance, right? If the model was created, who created this model? I wanted some sort of description of its governance. Who reviewed the particular model, right? When I create a particular model and I put it in staging, I put it in production, I put it in archive, who authorized to do that? And then, how do I integrate that with my local CI/CD? And that's the whole idea behind having a model registry, that you can actually have different versions of the model. And so the idea was that, what about we actually use a model registry as a central repository, whereby all the MLflow tracking server artifacts that we actually have can be part of the particular model. And the model registry is where people actually interact with checking out a particular version of the model or exploring what model is available, and the reviewer can actually check out a model in the CI/CD tool and make sure that that particular model is the one that was approved. And based on that, the people downstream can now look at the particular model and say, okay, this is a model in production, I can go ahead and use that. And so the model registry is a central repository that allows you to have named versions of the model. So for example, I have a registry that gives me all the models that I actually created. I can have different stages of the archive models. So this allows me to have the models to be in different production. I can have multiple versions of the model in the same stage. So this way it's important for me to look at two versions of the model and do an A/B testing to make sure that it works. I can load a specific version of the model. I can load a specific stage of the model if I actually want to use it, and then provides me the lineage activity of who actually worked on the model and how the model was actually developed over a period of time. And then the workflow is very simple. You have two sets of workflow. I can actually do the UI workflow, or I can actually do the API workflow. And the API workflow allows you to create versions of the model, update the model, delete the versions of the model, and so on and so forth. So there is a lot of documentation that allows you actually how to do that as part of it. And the idea is very simple. Model registry work UI gives you the ability to create a particular model, where the developer actually creates the particular model and runs it. Or you actually have the ability for them to register the model directly to the model registry by creating a version of the model. And then the MLflow registry work UI registry model can actually, person can check the particular model, run some test on it, and then either promote it to production or promote it to archive or promote it to staging if everything goes well. And then the person downstream can actually load this particular model as required. So the workflow is very simple. You have a model workflow registry UI that actually takes a model, creates a model into the model registry. You have the reviewers who can actually check out a particular version of the model to see on the version, and then update to a production if they actually require, if the test and everything passes. And then the downstream people can actually use the API to check the particular production model, and then run the automated jobs, can also check that model and then do the serving. So one example would be, I check in a particular model to the registry, the reviewer checks out the model, runs some tests, approves it, and the forecast model down can check that particular model out and run that as in production by just using the APIs to do that. So the workflow APIs is very important part of the registry. And again, just recap, it's a unique place to have all the model registered. You can actually have, you can do that everything through UI, or use the API if you are interested to do the operations in the API format. You have model versions where you can actually have multiple versions of the model in different stages. Model stages allow you to make transitions from staging to non-staging. And then it has a great integration with CI/CD integration, whereby you can actually check out a particular model in your CI/CD tool, run some tests, and if test passes, you can promote that model to the production. And then the downstream people can just load the tagged version of the production and then use that for inferencing. And recently, we actually added the ability to put tags and to a particular version of the model. So you can actually add a tag to it, to whatever tag semantics that you want to attach to it, and you can actually have search APIs that your management and ML ops can actually search that and then get the particular version and load that. So there's a lot of different ways to discover a kind of model based on tags, or based on version, or based on tags. And then there's a history of all the tags that were added and all the lineage of how the model actually went through from staging to production is actually needed. So the whole idea behind model registry is that we also have added thing called webhooks. So when you make a stage transition from staging to production, in your CI/CD code, you can actually call a particular webhook, and that webhook could be anything. You could load the particular model, run some validation test, send a Slack message. That part of webhooks is not part of MLflow open source. We are planning in releasing in 2.0 a plugin architecture. It's like we have deployment plugin architecture where you actually plug in your webhooks that you actually want, and you register your webhook with that particular stage. And then when we see that you have registered a callback function, we invoke that callback function. And then callback function is nothing but just an HTTP request to whatever you actually want it to do. So the plugin architecture allows you to customize your webhooks in a manner that you actually want to invoke a particular task or carry out a particular task based on the stage of the operation. Right now, it's not part of the ML open flow, it's part of the web, it's part of the managed MLflow, but we are planning eventually to have a plugin architecture that you can actually do webhooks with that. So that, in essence, is how you actually can do serving on the Databricks as well. You can actually take the model registry, keep a particular model, and then deploy it using model serving. Again, this is a new version of the model serving. It's not available, but on open source, you can use KF serving, you can use Seldom, you can use Algorithmia, you can use Redis. We have plugin architectures that people have written that you can actually solve. I think we are out of time, unfortunately. I would have loved to go through the tutorial for the registry, but it's there for you. If you have any issues, just send me a ping, send me an email message, send me join me on LinkedIn, and I'll try to respond to that. Are there any questions?
Thank you so much, Jules. Always.
Yeah, I know we were a bit squeezed on time. There's a lot of material to cover. This is normally a four-hour thing, but I hope I gave enough indications and enough rope for people to play with.
I was just going to say that we'll have to bring you on for a much larger workshop now.
Yes. I mean, like I said, this is a 4-hour workshop. It takes time to go through things, and it is important to really get to interact that. But I think when you have the in-person, I'll be in Toronto, and have a 4-hour workshop or a 3-hour workshop, so I can I don't have to rush through things, and it's a lot easier to do that.
Absolutely. We do have a question if you have some time.
Okay. Yeah, I'm looking at Jack. Is the backend, does MLflow registry store models in database like RDS? Yeah, for the managed MLflow backend, yes, we actually use the MySQL where the models where the model metadata is stored. The model artifacts are always stored in the S3 bucket. There's a distinction, right? There are two stores. There's a backend store for MLflow entities. MLflow entities comprises of run information, tags, webhooks, any meta information here, parameters, metrics, tags, data sets, log parameters, whatever you use to log that is actually stored in MySQL. The artifact store stores all the artifacts, and the artifacts are the model, a pickle file or esh file, whatever format it is, and any other artifacts. Let's say if you create images, or if you create a data dictionary that you actually want to store as a text file, or only SHAP images they actually create, those are the artifacts. Artifacts are stored different from, they're not stored in database, they're stored on the file system or an S3 bucket. I think, I think, right. Yeah, those are the only questions I had.
Mm-hmm. Totally.
Again, you guys have access to all the material. I mean, you can take your time to run through it. It should run no problem at all. The last module I have it, you can actually run in the notebook, in the Jupyter notebook. So I've given you instruction how to create a conda environment and run it. It should work, no problem.
Sounds good. Thank you so much once again.
You're welcome.
For a fantastic presentation and for your time.
And don't forget to attend Matej's talk on Thursday. Definitely.
Absolutely. Yeah. Sorry, just about that. Sorry for my confusion. So the talk's actually on Wednesday.
On Wednesday. Okay.
Yeah.
It's Wednesday. All right. Yeah, Matej. Yeah, attend Matej's talk. You can hear from the horse's mouth.
For sure. Thank you so much, Jules.
All right. Cheers.
Thanks, everyone. Once again, we'll be sending out the recordings after the summit. So thank you.